Alright gang, here we go. This is for Chem 2, Unit 11. We're talking about complex ion formation, a couple other things. This is it. You made it. Unit 11, almost in the bag. Just hang in there a little bit longer. I know it's been rough. So complex ions, we've kind of mentioned them very briefly in the past. What they are is that when you have a metal ion, it can actually act as a Lewis acid. So remember, a Lewis acid is an electron paired donor, and it'll form a complex ion with Lewis bases in the solvent. All right. So, and what these do is, if your metal ion that you're looking at can form a complex ion, then these salts' solubility will increase. All right. So these are a bunch of examples of complex ions and kind of how they work. Now, notice that they look complex and they form an ion. Yeah. So that's where they get their name. I know. I know. Okay, notice here we've got that KF thing. We talked about this previously in the video. Remember, KF is the opposite of KSP. So the KF, okay, is equal to the KSP inverse, okay, and vice versa, okay. Notice that it's the exact same thing but flipped around. We're just forming. Now, the one difference here is that it's not solubility, because the complex ion is soluble itself, but you know, just try not to look at it too closely. Anyway, so we've got silver and ammonium, and they've got their own naming and stuff like that. And it's complex ions are kind of a fun little bag of tricks, because they affect a lot of things, but they have very specific applications where they're kind of very important. All right, so here's a bunch of examples. Here's a bunch more examples of complex ion formations. You'll have to reference this table when you're working on practice problems. All right, so how does this actually affect solubility? Okay, so say you've got silver chloride here, and look, there's your silver chloride on the bottom. Some of it's dissolved. We've got one silver, one chlorine, but for the most part, it's insoluble. And then they're going to start adding a little bit of ammonia. Okay, and so as they add this ammonia, it'll react with the silver ions that are in solution. Okay, and so remember, your silver chloride, AgCl, is going to be like this. You got silver ions and chloride ions. And so as you add this ammonia, it will react with this chlorine, and this chlorine will start forming this complex ion. So the concentration of the chloride will be going down, therefore the reaction will shift to the right. So more and more of the silver chloride will be able to dissolve in solution. All right, and so this is the reaction that occurs. So this is the overall reaction. So silver chloride plus ammonia is going to form this complex ion, and then chloride, right? And it forms a new equilibrium. And notice it's actually quite a bit more soluble. All right, if we add enough NH3, all of it will dissolve. Okay, so silver chloride is insoluble, quite insoluble. All right, in the presence of the ammonia, the solubility greatly increases because of that complex ion. Amphoterism, okay, so amphoterism or amphoteric oxides, these guys are things that can act as an acid or a base, right? That's what amphoteric, right? We talked about water as amphoteric and all that. And so amphoteric oxides and hydroxides, so these are things that have oxygen or hydroxide, are soluble in strong acids or bases because they can act like the acid or a base. Big examples are these guys here: aluminum hydroxide, chromium hydroxide, zinc hydroxide, tin hydroxide, and their oxides as well, so aluminum oxide, stuff like that. They can act like an acid or a base. So here's an example. Here's aluminum hydroxide, pretty insoluble, okay, has a very low solubility, but if we add in a strong acid to this aluminum hydroxide, what happens is the aluminum hydroxide is going to start acting like a base. These hydroxides are going to come off, start to form water, so this guy will start breaking up into aluminum ions and then water in solution. So notice that he's all by his lonesome in there. Okay, all right. You don't have that precipitate anymore. It's just solution. Okay, and with the opposite can happen as well. So now we've got aluminum hydroxide, all right, going with these hydroxides, and this will actually form that complex aluminum hydroxide ion that we looked at on this table right here. Okay, this guy right here, 1.1 times 10 to the 33rd. That's really high. Okay, and so again, this aluminum hydroxide will react with this excess base that's in there, and it'll form this complex ion. And look, it's all disappeared again. Okay. We also have to be able to determine whether or not a precipitate will form in solution. This is actually pretty easy. All you have to do is look at your equilibrium. So we know that our KSP, right, is equal to the products, right? Concentration of the products raised to their thing. So if we have some insoluble salt that's like AB, right, this would be equal to concentration of A, and then or A plus B, right? something like that. We're just making things up, okay? And so essentially what we're doing is we're looking and we can decide, we have some KSP value and we can calculate the Q. So remember, our reaction quotient Q was different from our K because the reaction quotient was based on what you are at current conditions, right? So you can plug in your current conditions in order to figure out which way your equilibrium is going to go. And that's essentially what we're doing. So here's our big deal here. If your Q is equal to K, then that means your system is at equilibrium and therefore you have to have been saturated. So if your Q is already equal to K, no more is going to dissolve. Okay, so your solution is saturated. If your Q comes out to be less than K, then you cannot dissolve more solid. So you can dissolve more solid, so no precipitate forms. And that makes sense, right? If your Q is less than your K, that means you've got less products than you can have, right? You're not multiplying by big enough numbers yet, so your Q can get bigger. So therefore, you remember your K is your max. Okay, your K is when you're saturated. All right, now if your K is greater than your KSP, so whatever your calculated value is, your Q, your reaction quotient, if it's bigger than K, that means your products are too high. So therefore, you're going to have to form a precipitate in order for those things to fall out of solution. So these are pretty easy. You look at your K values, calculate your Q, right? Plug them in. If your Q is bigger than your K, you're going to get a precipitate. Anything less than that, you're fine. All right. So now this is kind of an interesting idea, is you can actually use these different principles we've been talking about the last couple of videos and stuff you've learned before in order to separate out ions from water. Okay, and so we can selectively precipitate out specific ions. So here they've got a mixture of zinc, copper, and they're starting to add in some H+. It's at a pH of 1. Okay, and then they're going to add hydrogen sulfide. Well, we know hydrogen sulfide is going to react with copper to form an insoluble solid of copper sulfide. All right, and the copper sulfide is going to start falling out of solution. So now our copper is going to be left behind. Or, sorry, yeah, our zinc is going to be left behind. Our copper is going to end up sinking to the bottom, right, with the sulfides. All right, and then we'll be left, and then we'll have a higher pH if we remove that copper sulfide and then add some sort of base to increase the pH. Then this hydrogen sulfide is going to start dissolving, and we'll get zinc sulfide in there. Okay, pretty interesting idea here. So we can use this next flow chart to kind of give ourselves a qualitative analysis. So this won't ever tell us exactly how much we have dissolved in solution, but what it allow us to do is actually figure out what ions did we have in solution. So if you have some solution containing unknown metal cations, you can add an acid to it, like sodium or hydrochloric acid, and if it forms a precipitate, you know it had to have been one of these three things here. Okay, silver chloride, lead chloride, or mercury chloride. Notice that the mercury is special duck. It always comes in sets of 2, right? Hg2 plus, Hg2 2 plus. It's kind of an odd duck. He's a diatomic cation. All right, anything that's left in there becomes this, and we can add hydrogen sulfide. We can precipitate it, decant, right? Decanting things is when you take off the liquid portion of whatever's above the solid. All right, and then you can get these guys when you add the hydrogen sulfide and then that silver or that hydrochloric acid. All right, and you get remaining cations, and you can just kind of keep working yourself through here, figure out what ions you had in solution. All right, anytime you have an alkali metal or ammonium, look at this at the very bottom. We could never get our alkali metals or our ammonium to precipitate. It's pretty interesting. So it still kind of follows the same solubility rules that we talked about several units ago, but kind of some new wrinkles. Okay, so that's it for Unit 11. We made it through to the end. I'm so proud of you. Thanks for hanging in there. Do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.